So, sometimes in math, we have to convert expressions to evaluate into different expressions to evaluate certain integrals. For example, you may not know what f of x, or the integral of f of x dx is, but, and this is a really cool but, you might know what the integral of f of g of t times by g prime of t dt. Now, the cool thing about this g of t is this g of t is actually going to be a composite function in itself, where this t is an inverse function. So t would be g inverse, and because we were originally in x's, it would be like g inverse of x. Alright, so now that we kind of understand what this is, it's really, we're trying to substitute in a trig function, which we know how to evaluate, and for things that we don't know how to evaluate. And then hopefully that helps us evaluate them. The reason why trig substitution actually is useful is because we have these three identities. 1 minus sine squared of theta is cosine squared of theta. 1 plus tangent squared of theta is equal to secant squared of theta. And secant squared of theta minus 1 is tangent squared of theta. So these identities are the entire reason behind us wanting to use trig sub. Trig sub is a very useful type of substitution. So in these examples here, we're given 9 minus x squared. So this is in the same form as a squared minus x squared. So we have to set, so our a squared is 9, so that means our a is 3. So x, I suppose I should be doing this in a different color. X is going to be equal to 3, and because we have 9 minus x squared, we're going to use sine of theta. Because now this will allow us to use the trig identity 1 minus sine squared theta is cosine squared of theta. What? We can't trade in x's for thetas because we can't evaluate an integral in terms of x, or an integral of x with respect to theta. So we need to find the derivative of this. So we get dx d theta is going to be 3 cosine of theta. Then we're going to multiply the differential d theta to the other side to solve for, d theta to the other side to solve for dx. So now we're left with this expression where x is equal to 3 sine theta and our dx is 3 cosine of theta. This is where we substitute in. So we put 3 sine theta and for x. So that gives us a 9 sine squared of theta. Alright, then down in the denominator, we're going to factor out a 9. So we get 9 times by 1 minus cosines, or not cosine, sine of theta. Sine squared of theta. And then this is being multiplied by cosine of theta, 3 cosine of theta, d theta. Well, now what we have to do is we're going to simplify this. So this becomes the integral of 9 sine squared of theta divided by 1 minus, we're going to just distribute the square root because the square root of a times by square root of b is equal to the square root of a times by b. It distributes, so we get 3, and in this case, 1 minus sine squared is cosine squared, so we can cancel the squares, and it just leaves us with a cosine of theta times by 3 cosine of theta d theta. Well, the 3 cosine of theta and the 3 cosine of theta will cancel. Alright, we are now going to be in a good spot where we can evaluate this. So we are now at the integral of 9 sine squared of theta d theta. But oh no, we don't know what the integral of sine squared of theta is. So what we do is we use some of our identities. We know that sine squared of theta is equal to sine squared of theta is the same thing as 1 minus cosine of 2 theta all over 2. Well, we can substitute this expression into the integral. So this becomes 9 times by the integral of 1 minus cosine of 2 theta all over 2. We're going to kind of break this down a little and just say that this is going to be 1 over 2 and cosine of 2 theta over 2. Well, what's the integral of 1/2 with respect to theta? That's going to give us theta over 2. What's the integral of cosine of 2 theta? That's going to give us sine of 2 theta, but we have to divide it by 2, and we're already dividing it by 2, so that gives us over 4. All right, now we have to get things back into terms of x's, so we have to solve for theta into terms of x's, and we use the original substitution to do that. So we get x over 3 is equal to sine of theta. That means theta must be equal to sine inverse of x over 3. We can now substitute this back into our integral. So we get sine inverse of x over 3 over 2 minus sine inverse, or sine of 2 sine inverse of sine, or of x over 3 all over 4. Now, in theory, you can use a double angle formula to evaluate this. But because it's in terms of x's, I do not feel like that is necessary. However, of course, it's always sometimes better to simplify, but I'm just not going to for the sake of time. All right. For this next integral, we are going to start out by completing the square. So, if we complete the square for this integral, we get the integral of the square root of x squared plus 2x plus 1 minus 1. So then this becomes the integral of the square root of x plus 1 squared minus 1 dx. I'm just going to set u in this case equal to x plus 1. So then du is just going to be equal to dx. This simplifies the integral by a lot. So this just becomes the integral of the square root of u squared minus 1. Now is the hard part. We have to substitute in a secant of x here. So we are going to say u is equal to, and because that's just a 1, we can just do secant of theta. So then our du will be equal to secant squared of theta d theta. Well, if that's equal to secant squared of theta d theta, this will become the integral of the square root of secant squared theta minus 1 times by secant squared of theta d theta. So now what we want to do is we're going to set this up to become the integral. The secant squared of theta minus 1 is the same thing as tangent of theta times by secant squared of theta d theta. Now we have to use another u substitution. So, I can't really delete the other ones or else I get lost a little. Gotta move things around, I'm sorry. There we go. Okay. Now what we have to do is we're going to say u is equal to or let's say w, since we've already used u. W is going to be tangent of theta. So then our dw must be equal to secant squared of theta, d theta. Well, solving for the differential dw, we get d theta, we get dw over secant squared of theta. Alright, so now this becomes the integral. The secant and the secant will cancel, leaving us with the integral of w dw, which will become a w squared over 2. W squared over 2 is going to be the same thing as tangent of theta. Tangent squared of theta over 2. Theta is the same thing as... Oops, looks like I got rid of it, but... Oh, wait, nope. Secant... So, we have to find... So, theta here is going to be equal to secant inverse of u. So, this becomes tangent squared theta over 2. Theta is the same thing as secant inverse of u. U is the same thing as x plus 1, so this becomes tangent squared secant inverse of x plus 1 all over 2 plus c. Always remember your constant of integration, even though I don't always remember it. Plus c up there as well. Alright, for this next integral, I think you want to start out with just a plain old u substitution again. We'll set u equal to x squared. This means that our du must be equal to 2x dx. Solving for the differential dx, we get dx is equal to du over 2x. So now we get 1/2 the integral of the square root of 1 minus u squared, du. This is an integral you want to use sign for, because we have 1 minus our variable. So, we are going to just say x is equal to sine of u. Or sorry, not our x, our u is equal to sine of theta. So then our du is going to be equal to cosine of theta d theta. We can now substitute this in, so we get 1/2 the integral of sine theta, or sorry, not sine, 1 minus sine squared of theta times by cosine squared of theta d theta. If you're smart, you'll recognize that this right here is a cosine squared of theta, so we're just going to cancel that, leaving cosine squared of theta square rooted. The square root and the square will cancel. This should just be a cosine of theta, but this becomes 1/2 the integral of cosine squared of theta d theta. We can now use our half angle formula. So we get 1/2 of the integral. Cosine squared is going to be 1 plus cosine of 2 theta over 2 d theta. So this becomes 1/2, and I'll distribute this 1/2 in there. So this will become theta over 4 plus cosine, or sorry, not cosine, because we're integrating this will be sine of 2 theta divided by, well, we're dividing this by 2 times 2 times 2, that would be 8. Now we just have to find theta. So, in order to find theta in terms of u, we just have to take sine inverse of both sides. So we get sine inverse of u is equal to theta. Well, what is u? U is x squared. So this is really just the same thing as sine inverse of x squared. And that is equal to theta. So we can substitute this in. So we get sine inverse of x squared over 4 plus sine of 2 sine inverse of x squared over 8 plus c, and that's the solution to this integral. All right, for this next integral, I am willing to bet that you may have thought that we were going to use substitution for this. And you would be somewhat right. We are going to set u equal to sine squared of theta. So then our du is or actually we're just going to set it equal to sine of theta. Sine of theta. Du is going to just be the same thing as cosine of theta, d theta. Or in this case it's d. I don't know why I was doing. Sorry, it's sine of t, cosine of t dt. So we clearly have the cosine of t. So this becomes the cosine of t, cosine, solving for dt. It's going to be du over cosine of t. The cosine of t will cancel with the cosine of t. So this becomes 1 over the square root of 1 plus u squared dt. Now this looks awfully similar to an inverse trig function, but sadly, it actually is not an inverse trig function. So we are going to use trig sub to kind of solve it. We are going to say that u is going, I want to do that in a different color, u is going to be equal to tangent of theta. So then our du must be equal to secant of theta d theta. Sorry, secant squared of theta d theta. So this is going to become the integral of secant squared of theta d theta over the square root of 1 plus tangent squared of theta. 1 plus tangent squared of theta is the same thing as secant. So this becomes secant squared of theta divided by secant of theta d theta. Well, the secant and the square, or one of the secants, will cancel the square root. So this just becomes the integral of secant d theta. Secant of theta d theta. All right. Now that we know that the integral of secant of theta, or we have arrived to the secant of theta d theta, what is the integral of secant? Well, interestingly enough, it does have a computable integral. The integral of secant, is going to be the natural log of the absolute value of secant of theta minus cotangent of theta. Well, we now have to get our original into terms of theta, or u into terms of theta. So if u is going to be equal to tangent of theta, that means theta must be tan inverse of u, and u is sine of t. So this becomes the natural log of the absolute value of secant of theta, which is tan inverse of sine of t, minus cotangent of tan inverse of tan inverse of sine of t and that would be our solution. Absolute value plus c. I just couldn't fit it there. That's a